Hey girls, sorry about that, I'm sick today, so this is the supplement for the lesson. I'm going to go through a few more questions on mathematical induction with the inequality with you. Some of them can be very challenging, some of them are pretty straightforward, depends on which one we go. So let's go with the first one. This is the one in your booklet. So prove 4n is greater or equals to 3n plus 7 for all positive integers n greater than 1. So because it's greater, be careful, n equals 1 is not the first case. The first case should be n equals to 2. So left hand side equals 4 to the power of 2, 16. Right hand side is 3 times 2 plus 7, that is 13. So that is left hand side is greater than right hand side. Let's check if that's right. Yep. Okay. So step 2. Test. Oops, sorry. Assume the statement is true for n equals to k, where k greater than equals 1 and k belongs to integer, i.e. assume 4 to the power of k is greater than 3k plus 7. Yep. Step 3. To prove the statement is true for n equals to k plus 1. That is, to prove 4 to the power of k plus 1 greater than 3k plus, plus 7. Okay, so as I said yesterday, if we were trying to prove left hand side is greater or equal to right hand side, we should actually move everything to one side in order to actually do something more to the algebra. In other words, in order to prove left hand side greater than right hand side, instead we'll prove left hand side minus right hand side is greater than 0. So in other words, left hand side minus right hand side equals, now I know this is a little bit different from what I wrote yesterday. However, you can change whatever you're trying to prove in here into the one we did yesterday, which is 4 to the power of k minus 1 minus 3 times k plus 1 minus 7. In that case, then you just start with left hand side because you have already changed your left hand side to that. In this case, I go straight from left hand side minus right hand side, excuse me, which is 4k plus 1 minus 3. Now, here we go, be careful. You have minusing everything, so you better just put a bracket in case you make a mistake. That is 4 times 4k. That's what we normally do. We split one out. And then minus 3k. That's plus 3 plus 7, which is minus 10. Okay, and now why do we need to split this again? Because what we did before, we have 4 to the power of k only. Now, if I replace the 4k by whatever in here, so about that should be greater or equals to 4 times 3k plus 7. We replace 4 to the power of k by 3k plus 7, but because the assumption set is greater, so therefore we have to change the sign to greater, not equal, just like what we did the other day. Minus 3k minus 10. Don't forget, from this line, you need to write from assumption. And then we continue. Now, as I mentioned today, you can keep writing greater or equals to. If you write equal, is that going to be wrong? It's actually not. The reason is not because we are just following this line in here. This line, if we keep evaluating, you can say equal. But because from the previous line you said it's greater than this line, whatever later on we write should be greater in the overall result. So it really doesn't really matter what you wrote. So I'll just keep writing greater than equal to, in this case, which is 12k plus 28 minus 3k minus 10, and should be greater than equals to, that is 9k plus 18. Now, since k is a number that is greater than 1, which is starting from 2, this is a positive integer. Whatever positive integer you subbed it in, this is strictly greater than 0. Since k is greater than 1, oops, I should change this then. My bad. And k belongs to integer. So therefore, left-hand side minus right-hand side is greater than 0, or equals to 0, because you started with greater than equal in here. Okay, therefore now we have step 4. The statement is true for n equals to k plus 1 if it's true for n equals to k. The statement is true for n equals to 2 by mathematical induction. It's true for n equals to 1 plus 1 equals to 2, n equals to 2 plus 1 equals 3, and so on. Therefore, the statement is true for all positive integer n greater than 1. Oops, mistake. 1 plus 2 equals to 3. 3 plus 1 equals to 4. So that's the end of this question. So that's how you actually solve that. Now, let's have a look with another one. Now, to save us some times, I will just copy some of these things and change the words. Please forgive me. My sound is just horrible. Okay, that's from here. So I'll do another question on the booklet, which is, I've already done 5. Now this time I'll do F6. So let the statement be 3 to the power of n greater than or equals to 2n plus n. For all positive integer n, starting from, this time is starting from 1. So this time we're starting from 1. So left hand side is 3 to the power of 1, which is 3. Right hand side is 2 times 1 plus 1. Oops, what did I write? Oops, 2 to the power of n. One plus 1, which is 3. So this case, left hand side is equals right hand side. That means the result is still true. Now assume is true for n equals to k. K is greater than or equals to 1. That is 3 to the power of k is greater or equals to 2 to the power of k plus k. Prove that it's true for n equals k plus 1. So that is 3 to the power of k plus 1 greater or equals to 2 to the power of k plus 1 plus k plus 1. Don't forget this is k plus 1. You also need to replace this k by k plus 1, not just the power. Okay, as usual, now we do left hand side minus right hand side. See if we can come up with a statement that is greater than 0. If we can do that, then we're done. Okay, so what do we have left hand side minus right hand side in this case is 3 to the power of k plus 1 minus 2 to the power of k plus 1 plus 1 in brackets. In case you made a mistake, just make sure it's in brackets. Okay, and then you can expand it now. So therefore, I'll split this as usual, minus 2 times 2 to the power of k minus 1. Mistake. Minus k minus 1. So now the assumption says 3 to the power of k is greater than this. 3 to the power of k is greater than this. So therefore, I'm going to replace 3 to the power of k again by 2 to the power of k plus k. But remember, since it's greater or equals to, you need to change this to greater or equals to, not equal. And then minus 2 times 2 to the power of k minus k minus 1. And then that is 3 times 2 to the power of k plus 3k minus 2 times 2 to the power of k minus k minus 1. So these two are like terms, which means is 3 of the thing minus 2 of the thing. That gives you just 2 to the power of k. 3k minus k is 2k. And then you got a minus 1 there. And now, since k is greater than 1 again, greater or equals 1 in this case, that means this whole number here has to be greater than 1, no doubt, because 2k is already greater than 1. So now 2k, you can write since k is greater or equals to 1, and k belongs to integer, therefore 2k minus 1 is greater than 0. And therefore, you can just write this statement. Therefore, left-hand side is greater than 2 to the power of k plus 2k minus 1 is greater than 0. So therefore, left-hand side minus right-hand side is greater than 0. Which have proven the result we wanted. And the statement is true for n equals to k plus 1 if it's true for n equals k, and starting with 1 this time. By mathematical induction, it's true for 1 plus 1 equals 2. Equals to 2. 2 plus 1 equals to 3. And so on. Therefore, it's all positive integer greater or equals 1. Okay, so that's the first two questions we have in here. We'll have a look at another questions later on.